Hello, everybody. So, this week you've been learning about Newton's three laws of motion, and I just want to review those so that I can um, hopefully clear up any misconceptions that you might have, answer any questions, and really summarize this topic. So, Isaac Newton, it's Sir Isaac Newton because he was knighted, was an English physicist and mathematician in the 1600s. So, these laws came around a long time ago. He is also one of the most influential scientists of all time, not only because of his laws of motion, but also for his theory of gravitation. All right, so he's the guy well known for the apple falling on his head and coming up with gravity. So he formulated the three basic laws of motion, and we're going to go over those today. So let's look at his first law, which is also known as the law of inertia. So inertia is a tendency to do nothing or remain unchanged. If your phone is on the table, it is going to stay on that table at rest unless something acts on it. Say someone hits the table. Say you pick up your phone. Now an unbalanced force is acting on your phone, making it move. But it's not going to move until that force acts on it. Okay? This soccer ball is going to stay at rest, stay right there on the grass until some kind of force acts on it. A kick. Maybe there's a strong breeze. Maybe somebody hits it with a bat. I don't know why you would have a bat on a soccer field, but it can happen. Unless some kind of unbalanced force takes place, inertia says that something that is stationary, not moving, is going to stay still. You sitting on a couch, you're not going to move until you put the effort in, you put the work, you put the force to get up off of that couch. It also says that objects in motion will stay in motion with the same speed and direction until acted on by an unbalanced force. This makes sense. Okay? If imagine there was no air, no gravity, or in outer space. You throw a ball in outer space, it's going to go on forever and ever and ever and ever until it hits something else. There is no force acting on it, so it's going to stay at the same speed in the same direction. Someone kicks a soccer ball, it's not going to stop unless a force is acting on it. Now, there's always forces acting on it in real life. As it goes through the air, it has air resistance. If it's across the grass, it's going to have friction. Or another player might put an unbalanced force on it by kicking it or stopping it with their foot or body or head. So things will stay in motion unless something acts on it. Now, the thing is, pretty much there's always some kind of force acting on it that will probably change something's motion. But if those forces didn't exist, they would keep on going. All right, satellites orbiting the Earth are a good example of this. So once a satellite is sent up into the atmosphere and it reaches where it's supposed to go, the top layer of the atmosphere, it is then going to go at the same speed around the Earth, orbiting it. It does not need to be using fuel at that point because it's no longer being pulled down enough from the force of gravity to bring it down to Earth. So it just keeps going in that same orbit over and over and over again without anything acting on it. Now, say a meteor came down, and on its way down, it collided with the satellite. Well, now that satellite is no longer going to stay in that motion. Some unbalanced force, that meteor, has now hit it and changed its direction and most likely changed its speed as well. But unless something acts on it, like a meteor, that satellite will go at the same speed in that orbit forever. Newton's second law, also known as the law of force and acceleration, tells us that acceleration of an object depends on two things: net force and the mass of an object. Net force is up here, mass is here, acceleration is here. So what this triangle means is that if we're figuring out force, we multiply mass times acceleration. If we're trying to figure out acceleration, we take force and divide it by mass. And if we're trying to figure out mass, we're going to take force, and divide it by acceleration. So that's how you use this diagram. Okay? So these all have a relationship with each other. So acceleration is produced when a force acts on a mass, right? You kick the soccer ball. The soccer ball has mass. You acted on it with the force, the kick, which causes it to start moving. That's acceleration. Now, the greater the mass of the object being accelerated, the greater the amount of force needed to accelerate the object. So say you have a soccer ball and a rock in the same shape and size as that soccer ball. Which has more mass? The rock. How do you know it? Try to lift it up. It's going to be heavier. So if you kick each with the same amount of force, that soccer ball is going to go flying. That rock is not going to go very far, most likely. Unless you're like Hercules, I don't know. So what that tells us is that there's a difference in the amount of acceleration that happens with a different amount of mass. All right? Because the acceleration is equal to the force divided by the mass. So the larger the mass with the same force, the smaller the acceleration. Think about it like this. If you are pushing a couch or pushing an exercise ball with the same force, that exercise ball is going to move easily. That couch might stay in place. There's too much mass. You're not applying enough force to make it accelerate. And that plays into inertia, right? It likes to stay at rest. Last is Newton's third law of action and reaction. For every action, there is an equal and opposite reaction. So this happens with a rocket taking off. So when two things collide, you're going to have each getting the same force in the opposite direction. Now, let's look at some diagrams. You have the gun here, and then you have the pellets. There is going to be the force pushing the pellets, and the same exact force is being brought onto that gun. That's why when you see guns being fired in TV shows, there's always that little kickback, the recoil. That's because the force is also coming the other way. Now, the bullets go extremely fast after with that equal force. The gun is being held by you, so that mass is combined. It's not going to then move as much. Looking here, this person is getting off of this canoe. When you step onto the deck and you are stepping with one foot and the other foot pushes off of that canoe is pushing you forward. So the canoe pushed you forward onto the dock, and the canoe then got pushed back by your foot, equal and opposite. Now, the same thing happens if you are standing on a rock and then you step on the deck, but a rock has a lot more mass than the canoe. So when you step off of it, the rock might not move because you did not put enough force to make it accelerate. Here, the rocket is standing still. There is gravitational force, the force of the rocket pushing against the ground, and it's pushing up. The ground is pushing up with an equal force. That's why it's not breaking through the ground or going up in the air. Then, as it's accelerating into the air, you have it pushing down in the air, and then that air pushing back up on the rocket. Air gets pushed down, like you see all that smoke get pushed down really, really fast. You don't want to be under it, one, because of the heat, and two, because of the pressure, the force of the air coming down. And then that air is also propelling that rocket up. Same can be seen here with the balloon. The action is the air rushes down out of this opening, and the balloon is then being propelled forward. So for every action, there is an equal and opposite reaction. If I'm talking about football, two players running right at each other, one has the ball and the other is tackling him. Well, the size of the players matters. Also, don't get me wrong, football players, I know it depends on how you tackle them too. But if one weighs 200 pounds and the other weighs 100 pounds, they're going to put an equal amount of force into each other, right? Equal and opposite action and reaction. But the one with the smaller mass is going to get a bigger acceleration, which means they might get pushed back really far. Their direction and their motion in their speed is going to go in a completely different way. All right. So those are Newton's three laws. I want you to just go and answer the questions on the Google form to show me what you learned this week.